just to pick a time, right? So request him to change the time, or do something, or have him do a review session, okay, for an hour on some time that works for everyone, okay? But you've got to use him properly. Because this is the second office hours, he sat through doing nothing, okay? Nobody came for both office hours, so on Zoom. So utilize them better, okay? All right, that sermon is over. Let's get going on action potentials, all right? So let me connect first. Any questions on anything I've done so far?
One question here.
Can you explain equilibrium potentials more? Or
That's half hour worth of block. Get more specific. What part of it is it that you're not understanding?
a good amount.
Okay.
Office hours,
Okay.
okay? Because that's going to take up a huge amount of time. So, but briefly, equilibrium potentials are voltage inside the cell, okay, that will prevent the ion from moving. The direction that the ion moves is important, because sodium moves inside from the outside, and potassium moves to the outside from the inside. So keep those separate, don't combine them, okay? So think about what voltage will sodium stop moving in when the inside becomes super positive. Positive repels positive, correct? Surprisingly, that's the place people get locked. You know like charges repel, right? You learned that 5th grade, 6th grade, at least, I hope. Fremont Unified? No? I went to school in Jersey. I mean, I had an amazing school, public school. I learned all this before I was born in Jersey. But we're talking California, 45th in the country for education. So a lot of people don't even know this. I'm not surprised. My physics students, they've never heard of this. And I'm like, you're kidding. Not your fault. So like charges repel. If you don't know it, nothing wrong with that. Write it down. Learn it now. Like charges repel. So if the inside becomes super positive, sodium's going to get repelled, right?
Yes.
When will potassium stop moving? If the inside becomes super positive, potassium will want to run for its life, correct? Because it's also positive. So what voltage will potassium want to stay inside?
Negatively.
When it's super negative. Those are the equilibrium potentials. Yes?
Yes.
Mark?
Yes.
Okay. All right. So let's go into action potentials. Okay. This is going to be heavy. It's very possible that that's all we do today. Possible. We'll see what happens. Okay, I guess that's all I can wish for. Okay. So an action potential, okay, is a cycle of voltage changes. It's a cycle of voltage changes. And I'm noticing from a lot of people's questions, you're not strong in your definitions. If you do not know your definitions and you're going to go on and study all these complicated concepts, it is going to be disaster, okay? You have to know your definitions. If you don't know your definitions, you have no right to go into the concept. Are we clear?
Yes.
So please, for heaven's sake, review your definition. Did you get into anatomy?
I'll talk to my teacher on Friday when her class is.
You're registered in her class. I saw her thing. So you are registered. So,
Okay, I'll.
So check it. And how many people are taking anatomy with this class? Good, like 3-4 people, okay? Be really watchful of your time, okay? These are two heavy subjects, okay? So please don't procrastinate on anything, okay? All right, action potential, cycle of voltage changes, okay, due to specific ion movements. Is there anything in this statement that's not making sense? Is there anything that's not making sense here? Voltage changes as ions move, right?
Yes.
So if positive ions move in, cell's going to become positive.
Mhm.
If negative ions move in, cells are going to become negative. Is that obvious?
Yes.
Okay. And I already, so let's talk about these changes. So any cell is going to be polarized. Do you agree?
Yes.
Yes.
Negative inside, positive outside. And roughly, this is negative 70 millivolts. Do you need to know these values? Absolutely. If I'm spending ATPs writing it, you need to spend ATPs shoving it into your cerebrum. Are we clear?
Yes.
And then facilitated diffusion into your exam. It's got to work that way, okay? Don't do bulk transport. No rote memorizing. That's not going to help. Polarized, okay? Cell is negative inside, positive outside. It's resting happily. Now, there is a stimulus, okay? Now, what is the stimulus? I don't know. It could be anything. It could be light. It could be sound. It could be some kind of a taste molecule. It could be stretching of a blood vessel. It could be shoving of a blood vessel. It could be, I don't know, just about anything. It could be a chemical. It could be a nerve, right? It could be electricity, right? Coming from somewhere, right? So it could be anything. Do you understand? It could even be a gas. Does that make sense? People won the Nobel Prize for showing that gases can elicit action potentials. So it could be just about anything that you can imagine. Now is not the time to specify what that stimulus is, because it could just about be anything. A stimulus in an action potential is defined as an event that causes depolarization. Okay? So definition of a stimulus, okay, is an agent / event, okay, that locally, very, very important word, it's the most important word in the definition, that locally, meaning what?
Within a small.
Only within a really small domain. Good. Only at that spot. Okay? Not everywhere. Does that make sense?
Yes.
Universally true. Okay? So that locally causes usually a weak depolarization. Okay? Because it always starts at a weak depolarization. When the first sodium channel opens, that's weak, right? That then causes more sodium channels to open. Are we clear?
Yes.
So it can become progressively stronger, but the very first event is going to be weak, by definition. And that makes a lot of sense. You want to open all the sodium channels at once, the cell's going to fry. Might make sense? It's to protect your cells. So it's got to be weak. Definition of a stimulus.
Agents or event that locally causes.
No, I'm not asking what it is. Are we clear?
Yes.
Use your sternocleidomastoid, right? Or your scalene, or certain digits. I don't care, but you got to tell me whether you get it or not. You get it or not?
Yeah.
Okay, Jesus, it's like pulling elephant testicles. Okay, so next event. So this is going to cause sodium influx. Okay, and how does that happen? The M gates flicker. Okay, the stimulus will cause the M gates to flicker. Are we clear?
Yes. No.
Okay, what are M gates?
Exactly. That's why I'm not clear.
Okay, so, well, please watch videos before you come. Okay, I know it's not required, but it helps. So M gates, what M gates are the parts of the sodium channel. Okay, so if you look at the sodium channels, right, here we go. So if you look at the sodium channels, so this is one part of the sodium channel. Okay, the M gate I'm showing in green. Do you see the green gate?
Yes.
Okay, so that's the M gate. And then the H gate, I'm going to draw in red. Okay, so the H gate is big and it's positively charged. This whole thing is one protein. Are you seeing this?
Yes.
Okay, watch my hands. Again, hands. You got two pillars that don't do nothing. They give you structure, right? They form the bridge, right? And in the middle, you've got your M gate. That's the white. Everybody see my pencil? I have a
Yes.
pencil? That's the white. and then I got a big tail with a big thing hanging here, right? A ball and chain that's hanging, and that's positively charged. Think about it. This is your cytoplasm, right?
Mm-hmm.
And this is your extracellular fluid. Everybody knows what those are.
Yes.
Extracellular fluid.
Outside the
I
cell.
heard it now. Extracellular fluid is the fluid outside the cell. Cytoplasm is intracellular fluid. It's inside the cell. Okay. So the cytoplasm is negative. Everybody knows that, right? At rest. So
Yes.
this big positive ball, is it happy in the cytoplasm or wants to run away?
Happy.
Run away.
If
Well,
you're positive and you're in an ocean of negative, what do unlike charges do? Attract.
Attract.
So the H ball is very happy in there. Are we clear?
Yes.
And when the M gate is not, M gate is a very thin gate. Are you visualizing this?
Yes.
Always use your hands. So M gate is very thin. It's like this, right? So when a stimulus comes in, remember stimulus is your first step. What that stimulus is going to do is it's going to push this gate down. Are we clear?
Yes.
The gate pushes down, one sodium goes in. Okay?
Mm-hmm.
That sodium is going to push the gate back up. And it's going to come like a pendulum. Come back down. Another sodium is going to go in. Back up. Down. Do you see it's flickering?
Yes.
The more sodium that goes in, the faster this flickers. Are we seeing this?
Yes.
Here's a relationship. I guarantee you it's on your exam. Write this down. The more sodium comes in, the greater the flicker frequency. Thank God we don't do essays. Usually this flicker is spelled wrong because my writing is so illegible. Flicker, F-L-I-C-K-E-R. Nobody got it. Okay, that's fine. Flicker frequency, okay? Everybody see this? So it starts flickering faster and faster. When M gate flickers faster and faster, what will be happening more and more?
More sodium.
More and more sodium comes in. Good. More and more sodium comes in, more and more flicker. Are you seeing this?
Yes.
So here's a really, really important point. If you have, so let's look at the extremes of stimuli, right? Let's say you have a really weak stimulus, and let's say you have a really strong stimulus. For example, somebody goes and stands behind my back, and they don't even touch me, right? They just do this. Now, if I'm super sensitive, I'll probably sense that, right?
Mm-hmm.
But if I'm one of those people, you have to beat me senseless for me to turn around, then I'm not going to sense that, right?
Mm-hmm.
I need a strong signal to activate my touch receptors. Is that making sense?
Yes.
So perception of stimuli is very, very contextual. It really depends on what you're talking about, where, who, what kind of context, right?
Mm-hmm.
If this room is really quiet, I could really whisper and you'll hear me. But if this room is going to be rowdy as heck, then you're not going to hear me. I have to scream on top of you. Clear?
Yes.
Yes.
So background, all of that's important. What is my point? The stronger the stimulus, the greater the M gate flickering, the initial flickering. Are we clear?
Yes.
I want everyone to write that down. I'm not moving forward until I see everybody writing this down. Stronger the stimulus, greater the M gate flickering. This concept was discovered so long ago. I do not understand why most of the textbooks don't use this and explain it clearly. Okay? The book I've chosen for you, it's the best of the lot. And even that does a lousy job. Okay? They call it the activation gate. M gate is called the activation gate. Okay? So when you read it, that's what it's called. I like the M gate because M means middle. So much easier to remember. Okay? Is everyone clear about this?
Yes.
You said the M gate is the line in between. What are the circle boxes again?
Those are the rest of the channel. So this entire thing that I've drawn here, the purple, the green, and the red, is one protein. Does everybody understand that?
Yes.
Yes.
That is a voltage-gated sodium channel. That entire thing is a voltage-gated sodium channel. Are we clear?
Yes.
Okay. So so if you have a weak stimulus, what happens? It flickers once, maybe one or two sodiums go in, right?
Mm-hmm.
but they're not strong enough to keep it going. Does that make sense?
Yes.
And the signal dies away. Okay? I'll get to that. It's called a sub-threshold stimulus, right? Sub means below, right?
Yes.
People also call it hypothreshold voltage, right? Hypo, lower. But sub-threshold is the more accurate word for it. Sub-threshold stimulus. But if you have a strong stimulus, what happens? You beat this hard enough right at the beginning that you get enough sodium in there to keep this going as a pendulum, right?
Yes.
Imagine a pendulum, right? If I give it a very slow force, it's gonna go back and forth, oscillate a little bit and stop, right? But if I'm gonna beat it, right? You know, I imagine that to be my mother-in-law and give it a good kick. That thing's gonna go all the way. Am I making sense? Nobody's recording this, right? Blackmail material. I'm sure she feels like that about me. So anyway, so it's gonna go a long way. Am I making sense?
Yes.
It'll hit the target. So that's the way to look at this. So if the stimulus is really strong, the initial M gate flickering is very, very strong, which translates to a lot more sodium going in right away. Yes?
Yes.
So you change the voltage right away and boom, an action potential. Action potential is like igniting a bomb. Okay? You need to have a strong ignition. Am I making sense?
Yes.
If your ignition is going to be weak, it's not going to light. It's going to start and then it's going to, fade away, right? It's not going to work. It's not going to explode, right? Action potential is like that kind of an explosion. And the sodium channels, the voltage-gated sodium channels, they are the matchstick. Am I making sense? They're the ones that light this action potential going, right? And to do that, you have to have a very strong stimulus. If the stimulus is not strong, M-gate flickering is weak, the signal fades away. So it's going to oscillate, come back to us. Am I making sense?
Yes.
So this state of the sodium channel is called, closed. Closed. It's very obvious, it's closed. Nothing can come in. The green is blocking the way, yes? Cannot name it any better. Closed. So when M gates flicker, right? So sodium influx, okay? And very, very important, this sodium influx, right? Okay? The flicker frequency depends on stimulus strength. Does everyone understand that?
Yes.
That yes is not strong enough.
Yes.
Okay, thank you. Flicker frequency depends on stimulus strength. The stronger the stimulus, the greater the flicker frequency. And the greater the flicker frequency, the more sodium goes in. The more sodium goes in, the greater the flicker frequency. What is this? Thank you, I heard it. How come when you don't understand something, you're all loud, and when you get the right answer, loud? Positive feedback. Of course it's positive feedback. Okay, it's a classic positive feedback. Where's the damn microphone? Are they kidding me with this? Alright. Anyway, I'm going to have to conserve my voice. Alright, once I did lose my voice during the lecture. Didn't happen. It's a 3-hour lecture, and then I lost my voice, and everybody got to go home. So, we'll see. Flicker frequency depends on this. So, I'm going to write down, this is a positive feedback. I can spell feedback mechanism. So, depolarization to threshold is a positive feedback. Depolarization to threshold is a positive feedback. I guarantee you this will be on your exam. Depolarization to threshold, some way, shape, or form. Depolarization to threshold is a positive feedback. So now what you do, follow along with me, is this keeps on happening, right? You will change your voltage from negative 70 to positive 63 millivolts. This number varies, guys. For some cells it's 55, for some cells it's 63, for some cells it's 65, right? Really depends on the tissue. This one is actually the one I measured in a squid neuron, physically in a squid neuron. So I use that number. So it's plus 63. You can really use any number you like. I don't care. There's no correct answer here. But if you want to keep your life simple, follow me. Yes, because this is what I'm going to ask on the exam, right? So 63 is your threshold voltage. Why? What's so special about it? Exclamation. Threshold voltages vary depending on the tissue. Also, horrible mistake. Negative 63, not positive 63. That'll fry you. Okay, you don't want positive 63. It's negative 63. Okay, so negative 63 is your threshold voltage. Everybody okay with this so far?
Yes.
Okay, what is the next step? There's a reason why we call this the threshold. I don't like that name because, to be honest, the older name was critical voltage. Critical, I like that a lot. Critical sounds negative, so they removed it, right? All these feel-goodies people, they removed it. They're like, oh, that sounds too nasty. Critical voltage is a much better term because that's exactly what this is. It's critical. The minute you hit that voltage, and I don't care what value it is, but the minute you hit threshold, okay, all the M gates start flickering at maximum frequency. When I say all the M gates, do I mean over the entire body?
Yes.
What is the definition of the stimulus?
Locally.
Hello, good morning. This is highly local. Do you understand?
Yes.
So all the few M gates that are there will now flicker at maximum frequency. So what is the definition of threshold? So let me write that out.
Critical.
Okay. So threshold frequency, this is the voltage that leads to maximum flicker of all local M gates. Now remember, M gates are part of what channel? Voltage gated. Thank you, Mark. Voltage gated sodium channel. What is another type of sodium channel? Voltage gated is one. What's another type of sodium channel? Often I get pump. Is pump a channel? No, that's a pump. Pump is not a channel, right? What's channel? What word should come to your mind when I say channel? Could be, but that's not the word, that's not universally true. When I say the word channel, what two words should immediately come to mind? Close. Channel doesn't have to be a carrier. Channel and carriers are different, right? Facilitated diffusion. Time to study. Okay? Facilitated diffusion should immediately come to mind. When I say pump, what should come to mind?
Active transport.
Primary active transport. Right? Primary active transport. Because secondary is not universal, right? Primary is universal. So I'm talking about facilitated diffusion. Do you agree?
Yes.
Yes.
Okay? So you open all these local M gates, they start flickering at maximum frequency. Here's a very important question, concept question. If I'm flickering with this is it. Beyond this, my hand's going to fall off, right?
Yes.
This is the maximum I can do. Do you agree?
Yes.
Which means I'm only letting what? 5 sodiums a second or 10 sodiums a second. Actually, people have measured it. It's about 4 sodium a second, right? That's the maximum we can do, right?
Mm-hmm.
So think about it. Can I say now that you've hit Tmax? Remember, Tmax is, it's in my lecture, right? Cell transport, maximum rate of transport. Have I hit my maximum rate of transport? Folks,
Yes.
what is maximum rate of transport? I can transport only so much. I've hit a plateau, right?
Mm-hmm.
Maximum is a plateau, right?
Yes.
So let me ask you this question again. At threshold, these are all exam questions. At threshold, M gates have, the sodium channels have hit Tmax. True or false?
True.
True.
Yes.
Write that down if you don't understand it. Go home and try to make sense of it. At threshold, voltage gated sodium channels. Look at how specific I'm being. At threshold, voltage gated sodium channels. Reach Tmax. And Tmax stands for transport maximum rate. And that causes fast depolarization. And the million-dollar question, what type of feedback is this?
Positive.
From negative 63, you hit the value of plus 30. Okay? So negative 60, so let me ask you this. From negative 70 to negative 63, what type of feedback was that? Positive. Negative 63 to positive 30, what type of feedback is this? What did I say about the question? What should you do to the question? Yes, you have to respect the question. You're not respecting the question, you're stomping on it. Why are you giving me vomit? Think. How is this positive feedback? You tell me. What is positive feedback? The response goes back and makes the stimulus even worse. Are you going back here at all? Okay, all the sodium channels open. You're hitting plus 30 really fast. Where's going back? Where are you going back? Where's back? Let me repeat my question now. Negative 63 to positive 30. What type of feedback is this? It ain't. It's not a feedback.
Yeah.
You're not using definitions, guys, and there's a reason why I'm saying this over and over. If you don't use your definitions, this class is over. You have to use your definitions. This is what should be instilled in you in 102. They don't do it, okay? So I have to do it here. Negative feedback means what? The response opposes the stimulus. Are you going anywhere near your stimulus?
No.
What are you doing to the voltage gated channels? You're hitting plus 30, right?
Mm-hmm.
Are you doing anything to it?
No.
No. Okay? So no, it's not negative feedback, it's not positive feedback, it's not feedback at all. It's a linear mechanism, right?
Yes.
A affects B, end of story. If I study, I get 100. That's it. That's not a feedback mechanism. Are we clear?
Yes.
Now, when that 100 makes me want to write harder tests, that's feedback. Am I making sense? Because it's coming back to me at the origin point. So please think before you answer any question. Think. Do not just jump to the answer. It's a very bad way of doing things. Okay? You should not do that in any subject. Okay? So you have to think before you answer. So this is not a positive or a negative feedback. In my 103A, 95% of students got it wrong when I asked this question. Because nobody thought. They went straight for negative feedback. They're like, oh, positive feedback is this, so this must be negative feedback. You should immediately follow that. That is a very lousy way of doing science. That means you don't know your definitions. You don't know what either feedback means. Or you're not applying it. It's even worse. So please apply and think about the question. Now, I want you to stare at this and tell me, is there anything here I can re-explain? You learned this cold. We're going to breeze through this class. Okay? Because you're going to see this in every lecture. Except immune system. Anything I can explain here? And this will all vanish as soon as you step out of this classroom.
Does the stimulus cause the Na influx, or does it make the gate flicker to then take in Na, to then take in the sodium?
You answer me. How can Na enter if the gates don't flicker?
The Na does not cause the Na does not cause the gate to flicker. It's the stimulus that does.
That's the first flicker. The Na then continues the flicker.
Oh, okay.
Right?
If it's strong enough.
Yes, that's why it's a positive feedback.
Got it.
Yeah.
In the textbook, it says negative 55 millivolts is the threshold, but we should just keep it at 63, right?
That value varies depending on which tissue you look at.
All right.
Okay. For me, since I worked on the squid, I always use negative 63. So they're not wrong. I'm not wrong. I'm just picking a different tissue.
Can you give an example of the stimulus for the MD?
I'm poking myself. Isn't this a stimulus? Right? So if I poke myself really hard, a lot more sodium goes in right away. If I'm just touching myself, only a little bit of sodium goes in. And if I touch too weakly, that's not enough to hit threshold.
Is the stimulus coming from outside the cell or inside?
That's a very, very good question. It could be anything. Majority of stimuli are internal. Majority of stimuli are internal. Outside stimuli are special. That's why we call them special senses. Okay? Vision, taste, all of these, right? Her question and my answer. Did that make sense? They're very important points. Okay. So I'll write that here for you. Thank you. So this could be external or internal. Right now, I don't care, right? They all do what?
They
This.
all cause.
Okay. Another obvious example. Let's say I take 1 crystal of salt. Everybody's seen 1 crystal of salt? Teeny tiny, right? Put it on my tongue. You can barely taste it, right? If I give you a teaspoon of salt, you can taste that immediately. Am I making sense?
Yes.
What is salt? Sodium. Right? So there, sodium is the stimulus. Are we clear?
Yes.
So sodium can be the stimulus too. In the case of taste. Is that making sense to everyone?
Yes.
So fast depolarization to threshold, right? Now, this depolarization here, okay, I have to specify that. This depolarization here, this positive feedback, is the slow dipole to threshold. I'll write this in a more organized way in a minute. Okay, so that's a slow dipole to threshold. So I want to emphasize this. Okay, and this is fast. And I want to emphasize all. Extremely important word. Okay? They're all turned on. Okay? That's the definition of threshold. Yes? Okay. Now, once you hit, I have to make a correction, sorry. Not threshold. Amplitude. That's what happens when I'm exhausted. Here. So, sorry, let me correct that. Amplitude. Amplitude is the maximum value. Now, at amplitude, your cell is plus 30, correct? Will this big ball be happy now? The inside is positive.
No.
Very positive.
No.
No. It wants to run the heck out like potassium. Correct?
Yes.
It wants to leave. So, what it's going to do at positive 30 is this. So, you're going to have this. Now, the M gate is going to flicker as usual, okay? So the M gate is going to be flickering. So I'm going to draw that as a dot. The M gate's going to be moving at its maximum speed. That's not changing, okay?
Yes.
Which means sodium is going to be allowed into the channel. Agreed?
Yes.
But what happens is the H gate is too big. And remember, it's positive. It's too big, so it gets stuck in the way. And we wanted it that way. All hell evolution, we wanted it that way. Okay? The H gate, and it's called H because it is your heavy gate. I like that name. Heavy. Call it what it is. It's heavy. Right? The H gate, it's also called the inactivation gate. Okay? That's not a bad name either. Inactivation gate. Okay? Because that inactivates the channel. The M gate is still flickering. Are we clear? Fully.
Yes.
Yes.
That's not changing. So the H gate, physically and electrically, blocks sodium entry. Let's do the electrically. It's a lot easier. The H gate is positive, correct?
Yes.
What will it do to sodium? Repel the heck out of it, right? So sodium can't come in. And the H gate is huge, right? Can you find your way through it?
No.
No. So here's an exam question. if the H gates are mutated, so listen to my question carefully and write this down. If the H gates are mutated, and if you're feeling very kind, put these questions on Discord, right? So people can think about this later. If H gates are mutated, right, so that H gate is no longer positive. Listen to my question carefully. H gates are not positive. Can they still inactivate the channel? Think before you answer. If the H gates are mutated so that they're no longer positive, but they're neutral, let's say, they're neutral, right? You replace the positive amino acids with neutral amino acids, right? So it doesn't have a big positive ball, it's a neutral ball. First tell me what will not happen. If it's a neutral ball, will it try, okay, to run out of the membrane?
No.
No. Am I making sense?
Mm-hmm.
So the result would be you get excessive sodium inside. Do you understand?
Yes.
And the cell will die. Okay? That's why evolution would never prefer something like that. You get eliminated. Cell will electrocute. Now for the fun question. What if you mutated it and replaced it with negative amino acids? Think and then answer. I don't want instant vomit. Think. And write it out and see what would happen. That way you're learning this concept. If the M gate at rest was negatively charged, what would be its effect on the action potential? It's very easy if you process it. Any guesses? Go ahead.
Will it burst the cell?
Why?
Because the negative would want to get out, because the cell is negative.
This doesn't burst the cell. One little domain is, a cell is huge.
Will it burst the protein? No?
If it's not going to burst it during a regular action potential, otherwise it's the same size. So no, bursting is not an option, but good guess. Yeah.
The gates will be closed, and the cell will not be able to depolarize.
That is absolutely correct. The cell would not have any action potential, right?
Mm-hmm.
But I disagree with the gate part. You have to be specific. Which gate? What
It will close itself.
What will happen to the M gate function if the H gates are negatively charged? Everybody understands this. If the heavy gate, that big ball, is negative, the cell is normally negative, right?
Mm-hmm.
It's going to want to run out. Elope to Vegas, right?
Yes.
That's what I used to call it. It wants to elope to Vegas, okay? But it can't, because the parents caught you, right? Make it drama, right? You'll understand. So it can't, because it's too big and it can't leave. So this will happen right at the beginning. Guys, if your cell is negative, right, and the H ball is negative, it's going to want to run out of there. I don't want to be here.
Yes.
Why is the H ball in the cytoplasm? Because the cytoplasm is negative and the H ball is positive. We're happy together, right?
Yes.
If we're both negative, that's it, I'm leaving. Too bad you cannot leave. And what's going to happen? The M gate will still flicker. And I did this experiment in squid neurons. That was my lab project for the semester. So I was able to mutate it and replace it. It was easy. Replace it with negative amino acids. And what happened was the M gate still flickered. Because the M gates are independent of the H gate. I don't care what you do. So you still respond to the stimulus. But can you have any sodium coming into the cell?
No.
No. So it's kind of pointless. Am I making sense?
Yes.
The M gate flickering does not result in a sodium influx anymore. Because the H gate is doing what?
Blocking the sodium.
Not block, just blocking. Look at the way I wrote it. Physically blocking. Thank you. It's physically blocking the sodium. Do you see how to think about this?
Yes.
Yes.
Everyone's like, is it too late to draw? and run out of this crazy guy. I promise you, this will become beautiful by the weekend. Okay? Especially when you supplement this with some nice vodka. Anyway, you'll start seeing the channels, okay? I remember one student at Berkeley said, you should supply us with some cocaine. So imagine these things. Anyway, so the bottom line is think of the different possibilities. Don't just sit there and eat what I throw at you. Am I making sense? You did that in anatomy. Those days are over. Okay? I want you to think. I say this big ball is positive. What if it's not positive? What if it's zero? What if it's negative? Right? Look at that biology. It's amazing. Correct? So H gates are independent of M gates. And M gates are independent of H gates. Are we clear?
Yes.
So it doesn't make any difference. If the H gates don't even move, but I made the cell positive internally, the M gates are not going to flicker. Does that make sense?
Yes.
But the H gate will want to run out of there. So these gates are independent of each other. They don't work with each other. Are we clear? It just happens, one comes after another, that's all. So people have shown that by experiment. And what does this dotted line mean? The M gates are flickering. That's what that means.
You said when you have a slow depolarization at threshold written on there, if the depolarization at threshold depends on the flicker frequency, if there's a stronger stimulus, wouldn't that create a faster depolarization at threshold?
Faster, but not the fastest.
Okay.
Fastest only happens after threshold.
So it's in relation to, okay. All
Yeah.
right.
I mean, it's like cranking an 18-car train. You're not going to hit speeds of 100 miles an hour within 2 seconds, right?
Yeah.
It's going to take time. Okay. So, everybody okay till amplitude? Do you understand what's happening at amplitude? The sodium channel is it's active as far as the M gates go, but it's inactive because no sodium is coming in. So another exam question. If the M gates were fully functioning, yes?
Yes.
Is that a guarantee that you'll depolarize? This is a very possible question. Very easy to answer. In other words, true or false, if M gates flicker, depolarization is unavoidable. False. Because here, sodium is not going in. Only if sodium goes in, you're going to have depolarization. Do you agree?
Yes.
Okay, so absolutely not. Not that this is important at all, but what do you think will be going on with potassium at plus 30? Think. Cells at plus 30. Potassium is what charge?
Positive.
Positive. What do you think potassium will be doing?
Leaving.
It's leaving a lot faster. So another exam question. Maximum, so leak channel. So listen to my question very carefully. Write every freaking word down. You cannot paraphrase these things. Potassium leakage channels hit their Tmax when?
At the end of polarized.
At the amplitude. Thank you. So at amplitude, potassium leak channels hit their Tmax. Because potassium is running for its life, right? But it's big, so its fastest rate is probably the same as the slowest sodium rate. Sodium is tiny, comes in quick. Potassium is huge. Plus, potassium is going to a positive charge, right? Remember that whole spiel?
Yes.
So, but Tmax is reached. You can see how I can mutate a simple concept into a god-awful question. That's a god-awful question, right? In fact, it showed up on one of the MCATs in 2003, this particular question, okay, that I wrote. It's the only question they ever accepted. They always reject my questions because they're too out of this planet. And this one was really out of the planet. But it's saying a very simple thing, right? So why does it look so god-awful? Because you don't have definition strength. So what should you do? Strengthen your definitions. When you see a term, immediately think, what does this mean? What does this word mean? What does Tmax mean? Oh, full speed. When will you get full speed? When potassium wants to run for its life. When will potassium want to run for its life? When the cell is at its maximum positive. And what is that maximum positive called? Definition again.
Amplitude.
Amplitude. No one's nodding off. That means this is good. Okay, so that's how I measure things. Okay, including me. All right, so is amplitude making sense? So you hit maximum voltage at this point, right? Next, what happens is very straightforward. You then start, this leads to, once you hit amplitude, okay, so voltage gated sodium channel inactivate, and I already babbled about this, right? Inactivated is the same as closed. Is inactivated the same as closed?
No.
No, because the M gates are flickering in inactivated, right? Guys, this is closed, yes? Look at where the M and H gates are.
Yes.
And this is inactivated. Are those the same?
No.
Draw it to know it. Draw it to know it. Have to draw it, okay? So they're inactivated, and then what you do is voltage gated. VG means voltage gated. Potassium channels open. Voltage gated potassium channels will now open. Here's a $1 million question. The sodium channel has all these bells and whistles, correct? Yes? I'm going to tell you that the potassium channel doesn't. It's a straight up elevator, right? The elevator doors open, potassium moves. Yes?
Yes.
Why? Why did evolution, is evolution unfair? You bet it's unfair, okay? It's called natural selection. Of course it's unfair. You have to be unfair. The whole point is being unfair. So question is, why didn't we evolve different gates for potassium channel? The most generic one, I mean, of course there's some really fancy ones. But the generic one doesn't have all these bells and whistles. No M gate, H gate and all. Give me some guesses.
Because we need to regulate potassium sensitively, so it's,
So shouldn't you have more bells and whistles?
so
Think, so when you're coming to that kind of a conclusion, remember that that you're passing a judgment on the pathway. That's not a reasoning. Am I making sense? And we all do this all the time. When we read tough questions, we do that. Right? We're like, wait a minute, especially why questions. And that's why why questions are hard in science, because you need to speculate based on the mechanism. Mark.
Is it because potassium is much larger?
And
Um,
moves much more slowly. Sodium is a bombshell. Yes?
Yes.
Potassium is not. Potassium is barely walking through the channel. Am I making sense?
Yes.
When you put bells and whistles, it's going to stop walking. Am I making sense? So you will actually defeat the purpose. Where the pathway has to be simple, it has to be simple. And where the pathway has to be really stringent, you have to be stringent. You cannot have customs at every McDonald's. You can have customs at the airport. Am I making sense?
Yes.
Sodium channel is like customs, because it's going to change the entire cell. Potassium doesn't do that. Plus, you also have potassium leak channels. That's another reason why we don't need these bells and whistles. So in evolution, potassium leak channels and voltage gated channels were probably together. And over time, they separated. The genes separated. Does that make sense?
Yes.
Yeah. So at amplitude, two events happen. Sodium channels, voltage gated sodium channels, are inactivated. The H ball sitting there. And voltage gated potassium channels, now they look like this, by the way. They look like this. They literally open. Are we clear?
Yes.
It's that specific voltage. Now remember, proteins are complicated, right? And they change shape, right?
Yes.
Right? So this one opens. Okay? So voltage gated potassium channels open, which will lead to what? Huh?
repolarization.
Yes, but give me an adjective. What would you add to that? Slow, thank you. It's a very slow repolarization, right? There is no other way. There is no fast repolarization, which means if you see those two words on the exam, what do? Kiss it, right? What do? If you see fast repolarization, what would you do? Cross it off immediately. There's no such thing. repolarization by definition is slow.
Yes.
Cannot be fast, no way. Are we clear about this?
Yes.
Okay. So you get repolarization. Okay? And repolarization here is very slow. This brings you back to -70. And this is very, very important. At -70, the sodium voltage gated channels are closed. They go back to being like this. Are we clear? -70 is rest. So tell me, if the sodium voltage gated channels go back to how they were at rest, can you start another action potential?
Yes.
Yeah. Yes, because now you can start the cycle all over again. Are we clear? Because you're back at rest. Isn't this a cycle?
Yes.
You're back at rest. But the problem is, now, if we had evolved that way, think about it. Action potentials would happen at an insane frequency, correct? That's not good for anybody, right?
Yes.
Right? Especially the brain that's receiving these signals, right? You're going to electrocute the brain. That's not gonna work. So, thankfully, potassium to our rescue. Potassium channels do not close until -84. They do not, and I want to use an analogy here. If you have a hole in your gas tank, right? Small hole, let's say. You just filled it up with gas, right?
Yes.
Right? But if it's going to be leaking, it's never going to be the same as having an intact tank. Do you agree?
Yes.
That's what's happening at this point, right? Because you're still leaking potassium, not through leakage channels, but through voltage gated channels, which are much bigger. So you're losing a lot of potassium. So voltage keeps dropping. So at this point, if you're going to have a stimulus, it better be a damn strong stimulus. Am I making sense?
Yes.
To reactivate the sodium immaturely. It's going to take a huge boulders to be falling on you for this to reawaken improperly, right? This gives rest to the cell. A few microseconds, but that makes a difference. Okay? The organisms that didn't have that, they probably died very early on and were made extinct by evolution, right? This is not a good way of signaling. So at this point, okay, potassium is still, it fluxes to -84 millivolts. And -84 is the what of potassium? Equilibrium potential of potassium. That's where potassium naturally stops, right?
Yes.
And it is the same voltage at which the channel closes also. Now, is that cause effect? No. It's just a coincidence. Are we clear?
Yes.
Evolution orchestrated it so that the channel closes when the ion stops. The door closes as you leave. If that happens on its own, then that's coincidence, not a cause effect. Make sense? Is that kind of an idea? So they both are programmed that way. So potassium effluxes to -84. This process is called hyperpolarization. Hyper means excessive, polarized means negative. Right? So this is hyperpolarization. Hyperpolarization is by definition slow. Why? Why is hyperpolarization slow? You involve potassium. Right? Potassium is
Yes.
always slow. So you go to -84. So at -84, okay, what happens then is everything is closed, sodium channels are closed, potassium channels are closed. Now think about it. If you're a threshold, I want you to analyze this mathematically. Normally your resting is -70, correct?
Yes.
Yes.
You have to go to -63 to get an action potential, correct?
Yes.
That's your threshold, yes? So you need to do 7 millivolts worth of work. Millivolts is a unit of energy. That's why you get billed for your electricity that way, right? Millivolts is a unit of energy. So you need to put in 7 millivolts of energy to get there, correct?
Yes.
Now, assuming you're at negative 84, right? If you have to get to negative 63, how many millivolts of energy do you need?
21.
Yeah, right? You need 21 millivolts, right?
Yes.
That's 3-fold more energy. Do you agree?
Yes.
So it's a lot harder to get to 63 from 84 than it is to get from 70 to 63.
Yes.
Everybody
Yes.
knows numbers, right? Makes sense. So this is 21 millivolts, right? Now what about negative 80 to negative 63? That's going to be 17 millivolts, right?
Yes.
So do you see, depending on where you are on voltage, it is harder or easier to get to threshold. Do you see that?
Yes.
Negative 84 is the hardest. Negative 80 is slightly easier. Negative 76 is even easier than that. And so on. Do you see how this is relative?
Yes.
This word's important. So hyperpolarization, the sodium channel is ready to fire, right? But it's going to be a lot harder to hit thresholds. Are we clear?
Yes.
So keep that term relative in mind. This is what the word relative means. Depending on where you are on the hyperpolarization voltage, getting to threshold is relatively easier and easier. Are we clear, or harder and harder? Whichever way you want to look at it. Okay?
Yes.
So I'm going to erase this because we don't need this. Okay. So potassium effluxes, everything stops, right? Now your best friend, sodium potassium ATPase, returns the membrane back to rest. Back to rest. And this phase is restoration. Now sodium potassium pump, is that a super fast mechanism?
No.
Sodium potassium pump. We did this Tuesday. Is it a super fast mechanism?
No.
It's a primary active transport. What did I say about active transporters are all
Slow.
slow? Why? Because they are all, what is that called? Definition. Transporters that have to change a lot of shape are called carriers. Because they're all carrier mediated mechanisms, this is going to be a slow process. Do you agree?
Yes.
That gives the membrane even more rest. Are we clear?
Yes.
So all our neurons, all the neurons that are involved in this, get plenty of rest. Okay? And that helps these neurons live their entire life. Because can neurons be easily replaced?
No.
You have whatever neurons you got is what you have. Are we clear? There's some exceptions. But the majority, you abuse it, you lose it. Okay? Everybody got that?
Yes.
Okay. So, and this is a very slow process. Are we ready to draw this? I'm giving you a minute. I want you to look at everything I wrote here. I don't know if I can make it tiny because you can't see it. Well, I guess you can. People in the last row, can you see all this? You're okay? All right. Well, look at your notes. You took notes. So look at your notes. 1 minute. Look at it. And then I'll draw it for you. Once you know all this, then you draw it. You're in good shape. Action potential will be at least 30 to 40% of your exam, minimum. Okay, and at least 20% of your lab exam. You're going to be doing a Physio X on action potentials. You should in fact just do it tonight. You just learned it, might as well get it done. Right? So the exercise on action potentials is due next week. Any questions on any of this? Okay, so I'm going to draw this for you. Whenever you draw a graph, you have to label the axes. Learn to properly draw a graph. Okay. So we got time in milliseconds. M-sec means milliseconds. That's thousandth of a second. Thousandth of a second. And this is millivolts, thousandths of a volt. Okay? 30 volts, okay, can kill you. Okay, just to give you a scale, right? 30 volts can electrocute you to death. So these are millivolts, right? So these are not that tiny. Okay. All right. So what is everybody? You have to do this with me. What is the resting voltage?
Negative.
Okay, so let's draw that. What is the lowest voltage you can reach?
Negative 84.
Negative 84. Let's put that there. Okay. And what is the highest voltage you can reach?
Plus 30.
Plus 30. Put that in red. Okay. What is another voltage that's important?
63. Negative 63.
Threshold, right? Negative 63. Good. So since it's depolarization, I'm going to use red, right? I'm going to put it. Oh, come on. Okay. So I'm going to put it very close. So it's negative 63. Everybody got the values?
Yes.
Okay. Don't worry about the time. Okay. The time is roughly 100 milliseconds, right? 100. No, not even 100. I think it's 30. Okay, 100 for cardiac muscle. It's about 30, right? 20 to 30 milliseconds. It's really quick. You don't need to know the time value, okay? Don't worry about the time value. So you're starting at rest, do you agree?
Yes.
So you're going, let's use this, right? So you're at rest, and then a stimulus hits, right?
Mm-hmm.
Now there are two types of stimuli. One's a really weak stimulus, right? So you can have a really weak stimulus that I'll draw using orange. Does that hit threshold?
No.
No, right? So it's going to fade. And you're going to see this in PhysioX. It's going to fade away. So this is a sub-threshold stimulus. Sub-threshold. Below threshold. Then you get a stimulus that's fairly strong that hits 60. Now tell me, you guys, is that rapid or is that fairly slow? Slow, right? Because it's a feedback mechanism, so it's slow,
Oh, yes.
right? If you're waiting for feedback, it's going to be slow, right? So that's a slow, and this is what we call a threshold stimulus or a critical stimulus or a supra-threshold stimulus, right? You hit threshold. When you hit threshold, what's the definition of threshold? Look at your notes and tell me. It's not a test. I just taught it to you. So look at your notes and tell me. Threshold, what happens? Maximum flicker of
Empty.
all the sodium channels, which means amount of sodium coming in.
T-max.
Huge. You hit Tmax. Thank you. Right? Huge amount of sodium coming in. Do you agree?
Yes.
So, boom. Do you see how fast that's going? Yes?
Yes.
Yes.
Rapid depolarization. Are we clear?
Yeah.
And then you hit threshold. At threshold, what happens? You have inactivation, right? No more sodium going in, potassium leaves. Now, what's going to happen? You're going to slowly repolarize, right? Won't be as fast as this. Do you agree?
Yes.
So you will repolarize. I'm drawing it very dramatically, okay? This one is dramatic. Doesn't happen this way. I'm drawing it like this to teach you something, okay? That repolarization is super slow. Everybody see that?
Yes.
Okay? And you come back, right? But you don't stop there. What do?
Go down to
Go
84.
all the way to negative 84, right? Everybody got that?
Yes.
And then you've got restoration. Do you see how slow that is?
Yes.
Everybody draw this. So this is what I want you to draw on a big sheet of paper and write all this information on there. Everything you know. And make sure that the repolarization is slower than depolarization. How can you show fast and slow on a time graph? If it's steep, it's really fast. if it's kind of shallow or not steep, that's slow. Okay, slower. Is action potential? This is one action potential. So going from rest back to rest is one action potential. Are we clear?
Yes.
Now, if you hit threshold, the action potential goes fully. It goes through all these stages. Can't stop it. Are we clear?
Yes.
You cannot skip steps. This is why action potential is all or none. Meaning, if you hit threshold, you will go through all the steps. You either go through all the steps or you don't go through any at all. Are we clear?
Yes.
How do I know all or none? So this is all, right? This is none, right?
Yes.
Yes.
All or none. No middle ground. Okay? You cannot have, oh, I go to amplitude and then I stop. Right? That doesn't happen. Are we clear? And
Yes.
this is a matter of few milliseconds. It happens extremely fast. Any questions on this graph? Everybody okay?
Yes.
One last concept on this, and then break. Okay, so I told you during this slow repolarization, I'm going to use blue. During the slow depolarization, sorry, the slow depolarization is a positive feedback, right? That's why it's slow, it's a feedback. So it's slow, and you hit threshold, and do you see threshold is a turning point, right? And then this is fast depolarization, correct? Rapid, in fact. And then you have repolarization, and so on. So let me ask you this question. Once you hit threshold, right? So let's say that the first row, 1, 2, 3, 4, 5, 6, 7, you're all working in my company, right? Your job is to make hats, right? And you make 5 hats an hour. Yes? You make 5 hats an hour. So when you start the day out, like we do at 7:30 in the morning, you make 2 hats an hour. You're like, oh. And then I give you coffee and donuts, and you're all happy. And then now you know at 10 a.m. you start making 5 hats an hour. I can bribe you to make faster hats at 7:30. If I bribed you at 1 p.m., all you're going to do is drink my coffee and donuts and still only make 5 hats an hour. Does that make sense?
Yes.
Because that's your maximum. Can't go more than that. Because voltage gated sodium channels hit Tmax at threshold, you cannot have a new batch of sodium coming in. Are we clear?
Yes.
You cannot go any faster. That's why it's a straight line. The slope is constant. Are we clear? So, and again, this is voltage, it's not rate of transport. Rate of transport will be a straight line, right? Because you hit a maximum. Which means, along this pathway, answer my question, along this pathway, anywhere along that pathway, can you generate a brand new action potential? Can you do this? A new action potential means new sodium channels should be opening. If 100% of the sodium channels are already fully open, where am I going to get a new sodium channel from?
You don't.
So if new sodium channels cannot be opened, answer my question, can a new action potential be generated?
No.
The answer is no. If you were to do nonsense like that, you would electrocute the cell. Are we clear? So these are all protective mechanisms. So anywhere from here to here, you cannot, absolutely not. Right? Just like how you ask me, can I get extra credit? What's my answer? Absolutely refractory period. Absolutely not. Right? You can't, it's physically impossible. Correct? That's why I said this word is really, really important. All the channels are opening. All my employees are caffeinated and working at full speed. Can I get 7 hats? No. 5 is all you get an hour. That's it. Right? Same thing happens here. So when I refuse to do something, okay, you say, why are you so resistant? Right? why are you resisting my ideas? Why are you resisting me, right? The fancy word, or all hail the queen word, is refractory. Okay, refractory. Refractory means resistant. I will not do it. So absolute refractory means what? I will not do it. I don't care how strong your stimulus is. No new sodium can come in. End of story. Are we clear?
Yes.
Absolute. There's no arguing here. There's no gray area. Is that making sense?
Yes.
I'll write that. Ooh, get a break. Okay, hold on. Not yet. I need to finish. I get a break. Okay, so absolute refractory period. I have given you slides on all this with textbook figures from a different textbook. Your textbook has different figures. This has different figures. All to help you understand this better. Does that make sense?
Yes.
I don't want to give you the same images as your textbook. That's stupid, right? I have access to another books. I use another books, right? And if they ask me, I don't know any of you. So absolute refractory period, because I shouldn't do that. Absolute refractory period. These guys are all crooks, right? Charging $300 a book. Absolute refractory period is what? This is the time, okay? No new sodium, and the key word is new. Okay? And the reason is between negative 63 to plus 30. The reason is all M gates are flickering at maximum rate. And what is that called again?
Tmax.
Tmax, thank you. All right, so no new sodium can come in. That part is clear, correct?
Yes.
Now let's analyze this portion. So what about from here to, okay, from here to here, right?
Yes.
So let's take the easy one. Here, at the amplitude, what is, use your hands, right? The H gate is blocking, remember?
Yes.
Can any new sodium come in?
No.
No. The voltage at which the H gate comes off the M gates, right, is when? Negative 70. Remember?
Yeah.
So from here to here, H gates are inactivating. Are we clear?
Yes.
So from here to here, can any new sodium come in?
No.
So no new sodium coming in here. No new sodium coming in here. Correct?
Correct.
So from negative 63 to negative 70, can you have any new action potential? I don't care how strong the stimulus is.
No.
Answer is not no. You have to say it dramatically like I do. What's the key term?
Absolutely.
Absolute.
Absolutely not. Right? Say it like that and you learn it. Absolutely not. Right? So this entire triangle is your absolute refractory period. Are we clear?
Yes.
Because no new sodium can come in. But notice, mechanistically it's different, right? Because in the ascending phase, right, sodium is coming in.
Yes.
You can't get no new sodium. In the descending phase, nothing is coming in. Are we clear?
Yes.
So it's like that. So is this making sense? The mechanistically very different. They're not the same thing. Even though the end result is absolute refractory period, they're being mediated by two different mechanisms. Are we clear?
Yes.
Appreciate the word mechanism. Okay, so that's absolute refractory period. What did I just do? Oh. I banged on the iPad, so it pasted that thing. Okay, it doesn't know what to do with me. Okay, now, what about the relative refractory period? I told you what relative means, right?
Yes.
Harder and harder to get to threshold, right?
Mm-hmm.
So I want you to focus now on this portion. So look and then take notes. Look at this portion. This is negative 84, right?
Yes.
This is negative 70, right?
Yeah.
So here I can generate another one if I want, but it's harder because potassium is still leaking, right?
Mhm.
So depending on where you are on this graph, the threshold, which is here, is harder and harder to reach. Are you seeing this?
Yes.
Okay? This is called relative refractory period. And simply put, what's happening, you're losing positive charge,
Mm-hmm.
right? So to get to threshold, you have to do extra work. Now, if you kept activating during the relative refractory period all the time, listen to my question carefully, respect the question. Remember Cartman, respect the question, respect my authority, right? So, that boy makes me laugh. Okay, so what's going on? The further and further I get down, that means more and more potassium I've lost. The harder and harder it is to get to threshold, right? To my goal, right? So that's why it's called relative refractory period. Now my question was, if you were generating new action potentials repeatedly during the relative refractory period, what would that do to the health of the cell? Is that good for the cell or not good for the cell?
Not good.
Remember, relative, R for relative, R for rest. You're trying to get the neuron some rest, right? Instead, you're not giving it the rest and you're electrically stimulating it over and over and over. That's not a good thing. Long-term stress does this to your neurons. Not all, some long-term stresses will do this. Okay? Abuse does this. Okay? Children, particularly in children. This was studied in children. So children undergoing long-term abuse, and I mean, don't immediately think sexual abuse or of that kind. These were children that had burns early on in life. And remember, burns is not just the pain they're going through, right? Also their appearance, right? Everything, right? Their whole life is stressful. Plus their body's undergoing internal inflammation for a very long time, because this kind of injury is really hard to get over. Okay? So, people have shown that. So relative refractory is meant to be restful. Now here's my other question. You're restoring here, right? By pushing potassium in and sodium out, right?
Yes.
Because you can easily ask the question, how come the voltage is rising? You're pushing sodium out. Shouldn't your voltage go down, right? No, because at this point, don't forget, you have the potassium leak channels working, and the pump, right, is pushing out. So remember, it's pushing out sodium, but bringing back potassium. Are we clear?
Yes.
So never assume that the pump and the leakage channel are working at the same rates. They can't.
No.
The leakage channel is a lot faster than the pump, right? Pump's a carrier, right? So that makes a difference. So the voltage very slowly comes back, okay, to -70. The reason for this is not only the pump, it's the sodium leakage channels. Here's where sodium leakage channels become critical. Sodium leakage channels will allow sodium in fairly slowly, okay? But they're still faster than the pump, right? So they bring in sodium faster than the pump pumps it out. Are we clear?
Yes.
So you go back to rest and then you will equilibrate. Are we clear?
Yes.
Now tell me, is it hard to get from here to threshold? From here to threshold? From here to threshold? Versus here to threshold? It is, right? You're at a lower voltage, right? This is all lower values, right? So this entire triangle is your relative refractory period. Are we clear?
Yes.
It's not so bad. Best way to master this. Sit down with your study partners. Each of you teach this to each other. I'm telling you, you learn this in literally 10 minutes. Even if you have to just read off of it, it's fine. In fact, that's how you should do it the first time, right? Because as you teach it to the other person, you will learn. Instead of just sitting there, not gonna help. I practice my lectures. I used to, not anymore. But I practice my lectures. If there's nobody there, I chain my dog and I sit down with him and make him listen. He just goes to sleep. Perfect. Any questions on refractory periods?
No.
No? Everybody okay?
Mm-hmm.
Look through it and see if you have any questions. I'll give you 2 minutes.
relative refractory period?
Sure. So relative refractory period. So now tell me, do you prefer PowerPoint or do you prefer this?
Yes.
And we're on time. We're not behind, right? We're supposed to cover action potentials today. We finished it, right? So it's not taking me far. That was one thing I was afraid of, is if I have to write and do this in my old hands, right? I felt maybe I'll go a lot slower than normal, because PowerPoint I can just point to things, right? I agree. I like this method a lot better. So relative refractory period is the time when a second action potential can be fired, but I'm going to be Queen of England, initiated, provided there is a strong enough signal. Okay, and this is relative to where the membrane is in terms of voltage, correct?
Mm-hmm.
And this happens from negative 70 to negative 84 back to negative 70. Correct?
Yes.
Please make that correction for absolute. Okay? So here, okay, H gates inactivate. So no new sodium influx. Right? Two different reasons, two different colors, two different reasons, right?
Mhm.
Why you have absolute refractory. Please study this tonight. Please study this tonight. If possible, maybe do the PhysioX tomorrow. Study this tonight and do the PhysioX tomorrow. Okay? But do it over the weekend at least, because that will really help solidify all this knowledge. Okay? This is the hardest lecture I ever give in physio. Always. Doesn't matter what level of class. Could be here, it could be a graduate level course. Action potentials are always the hardest lecture. So if you thought this was, oh my God, what is wrong with him? You're totally right. Okay? And this took me years to master. Years. And I'm still learning. I mean, there's still more to learn here. Okay? Anything else I can clarify?
Are you saying that it took you years to master what you just taught us?
Yeah. It took me
Do you
a
think
long
that's the best way to teach this class?
Huh? What?
Go ahead.
You don't want me to teach all this?
No, I'm just surprised that we learned in one day when it took you years.
I meant this concept. It took me years to master. I'm being honest. It's a hard topic. I'll tell you what happens when I don't teach all this. And I've done that in the past to high schoolers. They're confused as hell. They have no clue what's going on. Where I simply say, this happens, this happens, this. I could have finished this in 5 minutes. You realize that, right? By just outlining the events and saying, that's it. When you hit the heart and you're doing action potentials in the heart, and when you have action potentials in the pacemaker and in the cardiac muscle, that's when you'll thank me that I went through all these details. Because there's going to be a piece of cake. Make sense?
Yes.
So, yes, I enjoy teaching it this hard. Do I enjoy torturing you? Of course. That's my money there. But in all reality, in all seriousness, if you learn this well, this is your foundation, right? You're going to see action potentials in neurons. You're going to see action potentials in muscles. Hell, you'll even see action potentials in the ovum after fertilization. Shouldn't you learn this well? This is the most foundational concept here. This and cell transport. You need to know them. Okay? So I know it's daunting. I know it's intimidating. I'm admitting it. I told you it took me years to know. I could have easily just told you, oh, I looked at this and I mastered everything. right? You probably believe it, right? But no, this took me a long time to master because I had to think about it. I had to think about every step. Am I making sense?
Yes.
So if I didn't have the confidence that you will learn it, and 20 years I've been teaching this, people have been learning them, right? If I didn't have that confidence, I wouldn't teach it to you, right? I would just give you the high school version. A to B to C to D to E. I'll see you at the test. Right? That'll make you very confused. Now that you have all the pieces of the puzzle, it'll come together much better. Right? But you have to work at it. Nobody said you have to just you will just absorb what I blabber and you get an A. I never said that. You have to study. And on that happy note, you get your revenge. I have to drive 6 hours to LA. After 9 hours of teaching.
Oh, boy.
Okay, so anyway, so if I'm alive, I will see you tonight during office hours. Boy, this is a tough class. I'm seeing Rate My Professor coming up.
We love it.